All right. So this is chapter 18. Oh, I lost my pen there. This is chapter 18. And this is us moving away from our equilibrium into another process called electrochemistry. Right? And so electricity is involved with chemistry. Right? We see electricity because electricity is the flow of electrons. Right? And so we can see this in a chemical reaction because there can be a transfer of electrons between the atoms or the ions involved. So we see this a lot of times in single displacement reactions. We can also see it in combustion reactions. But there is also other ways we can see it. We can see it in synthesis. We can see it in decompositions. And so the important part to remember is the reason why we've been researching this is that chemical reactions that transfer electrons can lead us to cheaper and more efficient ways to generate electricity. This might be through fuel cells. These might be through batteries. And so we are very interested in electrochemistry currently because we have a big demand for electricity and we would like to make that more efficiently and cheaper than before. So electrochemical processes are any oxidation-reduction reaction, which means that we can either do this spontaneously, where we release energy, and that energy is converted to electricity, or we can use electrical energy to cause a non-spontaneous reaction to occur. So when you think about this, an oxidation-reduction reaction, you might have heard of it as being called a redox reaction. There's two things. It's either going to produce electricity when it goes through the process, or it's going to take electricity to drive that process forward. So the oxidation side means that that's the side that's losing electrons, whereas our reduction side means that we're gaining the electrons. So we can split every chemical reaction into two parts, our oxidation reaction and our reduction reaction. Now, the thing to remember is that when you lose electrons, you're oxidizing. So that's Leo the lion, right? Lose electrons, we oxidize. And then when you gain electrons, we have Leo the lion. And when we gain electrons, we're going to reduce. So when you gain electrons, you reduce, right? So Leo the lion goes grr. Right? Now, the hard part to remember with oxidation and reductions is that we're keeping track of the oxidation number. Now, the oxidation number is how we can tell if it's gaining or losing electrons in that process. And that change tells us whether it oxidizes or reduces. So when you oxidize, your oxidation number increases. And that means it becomes more positive, right? And it's becoming more positive because electrons are negative. So when we lose electrons, our charge goes positive. On the other side, when the oxidation number decreases, our electron or our charge should become more negative because we've gained more negatively charged electrons. Now, there's other ways that you can kind of tell what's going on. Sometimes it's about the number of oxygens or hydrogens. And so overall, what you really want to make sure that you practice doing is finding your oxidation numbers again, making sure that you remember how to identify oxidation versus reduction. So this is going to be a sample of an oxidation redox reaction. And so I want you to take a moment. I want you to identify all of the oxidation numbers for each of these elements in this reaction. Okay? And then once you have those oxidation numbers, I want you to answer this question. Oxidizing agents, which one is it? Which one is your reducing agent? And then we can walk through that. So there's a couple different rules that you want to remember as you go through with your oxidations. The first one that I'm going to do is I'm going to look at my oxygens. So any element that's in its elemental form, its oxidation number is 0. Right? So our oxygen over here is 0. The other part to remember that except for peroxides, our oxygen is almost always a -2 for the oxidation numbers. That's just the way things are. It has to deal with the electronegativities. There's very few times where oxygen is combined with a more electronegative element than itself. And so that's why it's almost always a -2. It could be something different if it was combined with fluorine, but we really don't see that. And the peroxides, that's the only other time where we see it, and it'll be a -1. Now, when we go through, if we look at our carbon, for example, with our hydrogen, this methane one, remember that hydrogen is going to be +1 when it's with non-metals and -1 when it's with metals. So hydrogen's a +1 there, and a +1 there. And so if our whole molecule has to add up to 0 for CH4, if we have 4 +1 hydrogens, then that means our carbon must be a -4. And on this side, if we have 2 -2 oxygens, then our carbon must be a +4. So when we're looking for things that change, that's how we're going to identify who's oxidizing, who's reducing between these. And so we can kind of look at this change of our carbon, and we want to decide, did we oxidize or did we reduce? Okay? So carbon went from a -4 to a +4, so it's definitely increasing its oxidation number. If it's increasing its oxidation number, then it's oxidizing, means it's losing electrons. On the other side, our oxygen, it's changed. It's gone from 0 to a -2. So that means that our oxygen, it's reducing in its charge or its oxidation number, so it must be gaining electrons. And so if we look at this, each oxygen is basically reduced and gains 2 electrons. Each carbon is oxidized and loses 8 electrons total, or each. And so if we have 4 oxygens going through that process with each one losing 2, we lose a total what's going on here? There we go. Total of the 8 electrons. We have 1 carbon and it's losing 8 by itself. So this is a total of 8 electrons gained. Total 8 electrons lost. And so we have 8 electrons transferred. Now, if we wanted to identify them as being an oxidizing agent or a reducing agent, remember oxidizing agents cause something else to oxidize, so you're actually reducing. So an oxidizing agent for this point is CH4, whereas our reducing agent means that we're causing something else to reduce. I confused myself with that already. CH4 is not our oxidizing agent. CH4 is actually our reducing agent. So our oxidizing agent causes something else to oxidize. So that means that it's our oxygen that's oxidizing, which I should have called earlier because that's exactly how it got its name as oxidizing. And our reducing agent is going to be the CH4 because it causes the oxygen to reduce. So the agent part makes them flipped. It goes in the opposite direction than what we had before. Now, there's a couple other practice ones that you can do for 7, 8, and I think this goes all the way up through 12, right? And then there's a little bit of a review on 13 about your oxidation reduction reactions. So make sure you practice those. The next part of what you want to work through is we want to do our half reactions. So in reality, your half reactions happen at the same time. It's not that one goes and then the other. But the nice part about it is we can split them into two separate parts. They don't physically have to happen in the same place. They can happen in connected spaces, kind of like in the fuel cell and electrochemical cell. Right? Now, when we look at it, this is our overall reaction up here at the top. And so we want to isolate the parts that are involved with the oxidation. So that's the part losing the electrons. And so in this case, it's going to be tin going from 2 plus to 4 plus. And it's going to be iron on the other side going from Fe3 plus to Fe2 plus. That's gaining electrons, so reducing. So the way that you can tell is you want to look for whether or not you have electrons. Electrons should be on the product side for an oxidation and on the reactant side for a reduction, depending on their process that they're going through, right? So if you're losing electrons, then you got to produce electrons. If you're gaining electrons, then you have to be putting in electrons in order for that to happen. And so when we balance a redox reaction, there's two ways to do it. You can balance it overall, but you have to also balance the electrons that get transferred between them. And so you can balance it by half reaction. So you break it down into which one oxidizes and then another for the reduction. You look at their electrons and then you balance each for its atoms. And then you balance the two half reactions for the electrons lost and gained. Right? So it's kind of like you do two balanced equations. You balance the atoms first for each one, and then you balance the number of electrons when you get to the end. And so you can kind of see an example of this on 16, right? They talk about how you do that. So balance your half reaction or assign your oxidation states, write out who's reducing, who's oxidizing, so you can get into the half reactions. Balance each half reaction first, and then you can balance the second part. Now, there are ways to do this with your water, your H2O, and your OHs, and so it depends on what solution you're talking about. So in this section here, they're describing the process if it's in an acidic solution. And so it's saying, oh, well, we might need more H's and O's inside of that process. And the reason why this happens is that some processes will pick up water and turn it into a proton, or pick up oxygen and turn them into hydroxide, depending on what solution you're in. And so if it's acidic, we know that we have lots of H plus extra left over. Right? So we can use that to help balance our H's. On the other hand, if it's a base solution, we have a lot of OH minuses, and so we can use a lot of our OH minuses. Right? So it depends on which solution you're in. Acidic solutions, you basically use water for your oxygens, you use H pluses for your hydrogens. If it's a base, you still use water for your oxygens, but you can use your H plus, you can neutralize it with a hydroxide. And so that's how you can balance your hydroxides on the other side. And so we'll work through some of that. So for this reaction, I want you to take a moment and go ahead and balance this reaction. And so this is going to be using our iron 2 plus, our permanganate, our iron going to iron 3 plus, and manganese. Right? And so you can use that to balance your way through. I'm going to go ahead and give you a moment so you guys can take care of that. So now we're going to go ahead and start. And so this is our chemical reaction up on the top. And so the first part is we want to make sure we've assigned all of our oxidation states. So our ions are our easiest ones. I always start with those. Their oxidation state basically lines up with their charge. Permanganate is kind of our one challenge. Right? Now it's got a -1 charge. Each of those oxygens is -2. And so that should give us a +7 charge for the manganese. And so if we wanted to separate this with our oxidation and our reduction, we can see that our iron is definitely oxidizing and our manganese is reducing. And so we can separate them into our two half reactions. Now, the challenge about why we have to balance our different half reactions is you can see that our permanganate has oxygen involved, but it doesn't have any oxygen on the product side. So we're going to have to add some water in for this reaction as we work our way through. Now, it doesn't matter whether you balance this as an acidic solution or a basic one, your coefficient for your iron is going to stay the same, right? And so in this case, we're going to go ahead and we're going to balance them by mass. And we're just going to assume that it happens to be in an acidic solution. So the first one, we don't have to worry about. It's already balanced by mass. So this one checks out. Now our second one, you can see that when we're looking at this, we're short oxygens from the left-hand side. So we're going to add in water to the right, which is going to be how we get those oxygens to balance out. So we needed 4 oxygens, so we added in 4 waters. Now that offsets our hydrogen, so we got to go back to the left, and then we got to balance that out with our H+. So we'll balance those with our protons. And so that's what it would look like when we balance it in a acidic solution. So now when we look at this, we can kind of see how our reaction kind of takes place, right? We have our 8 protons and our manganese going to our manganese +2 ion and the 4 waters. We do need to add in our electrons, so we know that we produce 1 electron through this oxidation. We need 5 electrons for that reduction. And so if we want to balance those, then we know that we need 5 times as much of that iron oxidizing as we do for that reduction of that MnO4. So overall, we need 5 times of that. We can add those two half reactions together, and so we get this balanced equation down here. Right? So when we go back to our question, it asks us which coefficient needs to be in front of that Fe2+, and we know that that needs to be 5. Because we have a transfer of 1 electron here. We have a reduction of 5 electrons here. So in order for that to balance out, we need 5 times as much iron as we need for that Mn. It's a little bit tricky, so you do want to practice those. There's another example where you can practice that, where we're going to be looking at our basic solution. And so I want you to take a look at this one. This one, instead of being iron, we're using iodine. And so I'm going to give you a moment in order to balance this one. And this time you're going to use a basic solution. So that means that instead of using the H+ in the water, you're going to use hydroxide and your water. All right. So we assign our oxidation states first. Iodine is a -1, Mn is still +7, right? Iodine has an oxidation state of 0, right? Our Mn is going to a +4. So we still have the reduction being the manganese, and we still have the oxidation being the iodine. We can separate it out into our half reactions down here. And then we need to balance them by their mass. So our first equation, we need to add in, sorry about that. Our first equation, we need to add in a 2 for the iodine. That way we have 2 iodines over here. Our second equation, we don't have to do anything because it's already balanced for everything but hydrogen and oxygen. And so the next one, what we need to do is we need to balance in our oxygens. So we know that we need 2 more oxygens on our product side. And so we're going to add in 2 of our waters. Now we add in 2 of those waters. That means that we need to get 4 of those H+ over here. Now, because we're doing this in a basic solution, right? So far, everything has been the same as if it was acidic. And so if it was acidic, we could have just stopped right here with this equation for our acidic. But instead, because it's basic, what we're going to do is we're going to neutralize them. Right? We're going to add in hydroxide to the side that needed H+, turning it into water. We're going to add in the same amount of hydroxide to the other part. And then we can consolidate them. So we need 4 waters on this side with 3 electrons. And then on this side, you need 4 hydroxides and our 2 waters. We can balance our electrons for their charge. And we could also remove any of those extra waters. So we can consolidate this down. We can see that we need twice as many of our bottom equation, so that way we can transfer 6 electrons. We need 3 times as many of our top equation, so that it will transfer 6 electrons. And when we add those together, once we remove those extra waters, we get our final reaction down below. So it's a little bit of a roundabout way to go through this. Basically, your book recommends balancing it like it's a acidic solution first, and then neutralizing your acid with water. And that's a fine way to do it. You can also remember that if you need hydrogens, add water to that side. If you need oxygens, add hydroxide to it. But they both work, right? So it doesn't really matter which way you do it. You just want to make sure that you remove those extra waters at the end. And so when we go through all of that process, we have our answer down here at the bottom, and then there's another one where you can process that, or you can try that. And so this is looking at chromate with our chlorine. All right, so now that we've practiced balancing our chemical reactions, we're going to move forward into a little bit of a talk about what an electrochemical system looks like, right? And so electrochemical systems, there's a couple things about how we measure them. Right? One is we measure them in terms of their current. So current is the flow of the electrons through a conductor. Now that flow depends on the amount of those electrons are moving. So it's not about how much energy the electrons have, but it's actually the physical number of electrons. So electrical current is the amount of electrical charge that passes a point over a given period of time. So it's kind of like the number of electrons that flow through it. Right? So they could be moving slow, they could be moving fast. It's just about the amount of charge that's in them. So since redox reactions involve the transfer from one substance to another, then they also have the ability to generate a current. Now to use that current, we have to separate where the oxidation is occurring from where the reduction is occurring. So that way, if we make electrons over here, we can make those electrons travel across to where they're going to be used for the reduction. And so in this period over here, we would have some current. So electrochemistry is kind of the study of redox reactions that produce or acquire electrical current in order for that to take part. Now this happens in what we call as an electrochemical cell. Right? And so that's when we convert that chemical energy and that electrical energy. Right? Now a spontaneous process is called a voltaic cell or a galvanic cell. But basically, a spontaneous one is kind of like a battery in that it's going to produce energy or electricity. Non-spontaneous ones are what we call an electrolytic cell, and then, or electrolysis. And we're going to be putting electricity into those systems to make them go forward. Now, to do this, we always have our oxidation and reduction half reactions occur in 2 separate parts of our cells called half cells. So you can kind of imagine that you have one container over here that's doing all of your oxidation. And then we would have another container next to it where we do our reduction. So we connect those two things by a wire, and that wire connects one solution to the other for the electricity, the electrons to flow through. And then inside, in between, we have to have somewhere for those ions to move between those two systems. And so they occur in something called an electrolyte. So because those two oxidation-reduction reactions don't have to physically be in the same place, we actually want to keep them separate so that way we can force the electrons to travel along our wire so we can use it for electricity. Then we're going to connect them with some electrolyte to help those ions flow back and forth between them to balance out that charge. So we've talked about oxidation, we've talked about reduction. And so remember that an anode is going to be where our oxidation occurred. All right. On the other side, we have an electrode called a cathode, and this is going to be where reduction occurs. All right. Now, one way to remember this is reduction happens with a red cat, whereas oxidation happens with an ox. All right? So you kind of have two animals to remember. You have an ox and you have a red cat when you're trying to connect your electrodes. So your anode is going to be for oxidation, your vowels with each other, and your cathode is going to be with your reduction. So over time, your anode is going to be connected, is going to lose weight in the electrochemical cell generally, right? Because it is going to go through oxidation, it's going to lose its electrons. Your cathode is going to gain weight, it's going to gain those electrons, and so we're going to plate out material. And so this is a picture of a cell, and so it's kind of like a battery. We've separated them into their two pieces. We have our anode, which has one material. We have our cathode, which has another. They're connected through this wire where electrons are going to travel. And you can see that those electrons are going to give away some of their energy to that light bulb to make it glow. Now, while all of your electrons are flowing in one way, we have to have our ions, our positive ions flow, or our ions flow in the opposite way to replace them. And so that's what we get with this thing called a salt bridge, is that it's going to help us balance the charge. Because as more electrons get in here, this side is going to become more and more negative. As more electrons leave here, this is going to become more and more positive. And so we're going to use these ions to help balance out that charge. So a zoomed in version of that, you can kind of see how this cycle flows. Our electrons are moving from this manganese over to our nickel as those processes keep on going. And so that's how our system works between those two. Now, for our anode, with this one with the zinc, each of those zinc metals is going to zinc 2+ ion, so each one is losing 2 electrons. And on the cathode side, our copper ions that are in solution, they're each gaining 2 electrons to turn into copper metal. So we have an oxidation, and then we have a reduction, and together that's going to be our complete cell. So look at these and try to identify which one could take place at the anode of our electrochemical cell. So which one could take place on the anode portion? So if we're looking for an anode, we're looking for an oxidation. So if we're looking for an oxidation, we should be increasing our charge. So our nitrogen in this case is a +2, and it's moving on into a +5. Our vanadium in this case is a +5, moving to a +3. No, +4. Our oxygen is going from a 0 to a -1. So if we look at this, this one is an oxidation, this one is a reduction, this one is a reduction. And so the only one that could function at the anode is going to be these two. Sorry, it is that one, our nitrogen monoxide going to a nitrate. The other two would be good for a cathode as they go through a reduction. Now, think about why do we have to have a salt bridge? So we know we have to have the wire for the electrons to travel, but why do we need to have the salt bridge? What are those ions doing? And so when we had our two containers and we had electrons flowing from one side to the other, those electrons have some charge with them. And so if they have charge, that means that charge is slowly building up on one side, negative for where the electrons are going, positive for the anode side. And so eventually that process is going to work against itself. It's hard for us to put negative things where there's negative charge. And so we're going to get this separation of this charge. So we use this salt bridge to add in ions to help balance that out. We use the salt bridge to add in positive ions over here and negative ions over here, and it keeps each of those half cells neutral. So it's not that we need a source of ions to react, right? Each of those solutions with the electrolyte, they have all of the ions they need. It's not that we need oxygen to facilitate, or we don't use it for the electrons to travel. Really what we're using it for is to maintain the neutrality of the half cells. So you need the movement of ions, so that way one side doesn't become really negative and the other side doesn't become really positive as that system runs over time. And so now for our next one is I want you to take a moment and I want you to build out what your battery looks like. Right? So one side is going to be aluminum going to aluminum 3+. The other side is going to be copper going to from copper 2+. And then we're going to fill in our other pieces. Right? So I'm going to help you out with this first part. This box here is going to be for your reaction. Of what's happening at the cathode or the anode. This part up here is going to be what is the material. And this is going to be what is in the solution. So if we wanted to, we want to look at this track of our electrons. So our electrons are going from the left-hand side to the right. So that means that this one must be our anode because it's producing the electrons. This one must be our cathode because it's gaining the electrons. So when we look up at the top, we want to line up our anode process and our cathode process. So take a moment and go ahead and do that. So now when we're doing this one, we can look at our anode process. So between our main chemical reaction, our anode is going to be our aluminum. And so that metal should be aluminum as a solid. And in our solution, we should have Al3O+ as ions, because the oxidation is the aluminum going to the aluminum 3+. On the other side, we're going to have our cathode. Now, our cathode is going to be our copper as a solid. The ions will be copper 2+ in its solution. And it's going through a process where it's going from copper 2+ plus 2 electrons to copper solid. And so our battery looks a little bit like this. Go ahead, take a moment. You can do the same thing for this nickel and this lead as you try to fill in which one is traveling from where. A chemical reaction should look a little bit like this. We have our anode on the left, we have our cathode on the right. And so we're traveling from one side to the other. Our nickel should be our anode because it's the one oxidizing. Our lead should be our cathode as it's the one reducing. And so that's what we should be having for those. And so this chemistry is really the way all of our battery systems work. So when we talk about lithium-ion batteries, we're really talking about them being made up of some type of lithium anode, right? So it's got lithium metal, and then that's going to convert into some other material. On the other side, we normally have something like cobalt as a cathode, but each battery has a slightly different setup. So we have a positive side where we're going to get some energy out. We're going to have a negative side that we're going to connect to for our to complete our circuit. And so our electrons are going to flow from this negative side to this positive side over and over again as we try to drain that battery of its electricity. So during discharge, this is when we're using the battery to get electricity out. The lithium, those ions, they give up, or the lithium atoms, they give up electrons to turn into lithium plus. And those electrons would travel over to the right-hand side, and they reduce, in this example, cobalt to bring that down. Now, the interesting part is once that the lithium has turned into lithium plus, those lithium ions actually migrate over to the cobalt to help balance out that charge. And then when we're ready, when we recharge our lithium ion battery, we slowly convert that lithium plus back into lithium solid. And so those lithium will migrate back into that graphite where they become lithium metal, and they'll be ready for our next discharge. So over time, we kind of have this rocking chair impact of our lithium going in one direction when it is releasing energy, going in another when it's gaining energy. And that's how we can make our battery work. Now, not all batteries are equal to each other. When we talk about batteries, there's three things that we talk about. We talk about voltage, which in some cases is called potential. We talk about current. And then we talk about reversibility, right? So some reactions give us a lot of current and a lot of voltage, but it's very hard to reverse, right? And so they're good for certain applications. Other ones are very easy to reverse, but they don't give us much current or they don't give us much potential. And so that's for a different type of process. So as we work through that, then we're looking at those two things. So the first one is, let's clarify what's the difference between voltage and current. So the potential difference between the two electrodes, this is the driving force of the cell. So the stronger that difference is, then that's this voltage, the push or the strength of the water, right? Or the electricity. So if you imagine that this was like a hose, your voltage is how strong that water is when it comes out. Is there a big difference between them, or is it a small difference? So all three of these systems have the same voltage. Their difference from high to low is the same, and so they're going to come out with the same amount of force. Your current is the amount of charge that passes. So when we look at our current, it's kind of like the nozzle at the end of your hose, right? A smaller nozzle will restrict your current more, and so you guys won't get as much water to flow out, whereas a larger current will have a lot of water over that same period of time. So it's kind of like a garden hose versus a fire hose. Even if they both came out with the same amount of force, your fire hose just has a lot more water coming through it in the given same amount of time. And so it's got more current, even if the force was the same. So current is defined as an amp. So its unit is an ampere. Now an amp is really the amount of charge per second that's flowing. And we call it a coulomb because a coulomb is the charge of 1 mole of electrons. So an amp is defined as 1 mole of electrons traveling per second through that period of time. Now, current is generally dictated by the size of your battery. The larger your battery size is, the more current flows. And so the difference between a C battery, a D battery, a AA battery, or a AAA battery, all of that isn't really their voltage. They all use the same chemistry or very similar chemistries to do that process. What's different is the size of their surface area, and so they produce different amounts of current. They also might have different charges inside. Voltage difference, it's also known as our potential. And so we're going to talk about potentials a lot with them. It's going to be the difference in energy between our reactants and our products. Okay? So this is how much energy each of those electrons has to carry for that process to go forward. And so we measure that in the form of a volt. And the volt is equal to 1 joule of energy per mole of electron of charge. Now this force that you can kind of imagine, this is called that EMF, or the electromotive force. So the stronger that difference is, the stronger its EMF, the more it can do between those. Now, for our cells, we're going to generally talk about them in terms of potential, right? So potential is going to be tied in with our voltage. Now the cell potential basically depends on how easy one thing oxidizes versus the other one reducing. And so that difference between them, we call it the standard EMF if it's at standard conditions. And it's giving us an idea about that energy in terms of potential or voltage between those two. And so we're judging them based on their different processes, their chemical reaction. Are they easy to do or hard to do? And so for our cells, there's a notation for them. Oh, I forgot we didn't talk about our standard conditions. Standard conditions, 25 degrees Celsius, so similar to what we were doing for thermodynamics. 1 atm for gases, 1 molarity for concentration. Just like Hess's law, the sum of the cell potentials for the half reactions is equal to the sum of the cell potential is equal to the sum of their half reactions as well. Right? So we can kind of add them up or break them apart as we see. So our cell notation looks a little bit different, right? And so this is what we do in order to make it in a shorthand way for us to write out what's going on. It always starts with the oxidation on the left and the reduction on the right. And so generally speaking, when you see our diagrams are almost always ox and then reduction. And so as we move from one to the other, one side of your equation is held together by one line. Then you have this double bar, which is kind of separating them apart from each other. And then you have another single bar with your electrodes. So you can kind of imagine that this is all one cell, and this is the other cell as you guys work your way through. So the single line is kind of saying it's a phase barrier. So it's going from a solid to a liquid. So that's why our electrodes and electrolyte are different. The double bond means that there's a salt bridge. So that means that they're connected, but they're connected in that there's the ability for ions to transfer, but they're not in the same system all mixed together. Now, if we have multiple electrolytes, then we might see commas used on one side of the bar over the other. Or if there's no electrode, we might see something like that. Or you could even see something like our FeCl2 and our FeCl3 for a reaction could look something along those lines, where we have kind of like our cathode, or what's going to stand in, as our anode, is the +2 version, and it's going to be oxidized to our +3 version, right? And so we can do that. Normally what that means is we use an inert electrode. So looking back at our example of our cell with our zinc going to our copper, right? We're going to draw out the cell notation down below. So we have our oxidation down here. We have our reduction over here. This is going to be kind of our anode, so what we start with. This is what's in the solution. On the other side, we're doing our solution, and then what we end up with on our cathode. And so you can kind of imagine that these were both our reactants, what we started with. This is both our products, what we end with. And that's kind of how you can align those to be correct. So your two anodes and cathodes go on the far sides. Both solutions should go on the middle. You should always include your states with them, so that way we can keep those connected. Now, typically for your electrodes, it's almost always a metal for our anode, and either the same metal that we're reducing or something similar for that on our cathode. Now, we're primarily using metals because we're transferring electrons, and so metals are easy because they do move or allow electrons to move, and so it makes it a little bit easier for our process. Now, if they might be using just ions, so we might not be using a solid, it is possible that you can use an inert electrode. So this is going to be something where its job is just to give electrons and receive electrons, but not actually take part. We see that often with platinum, or sometimes iridium is kind of like a way to do it. You can also do this with silver, gold, as well as cheaper graphite electrodes as well. So it depends on what situation you're doing, but those are all common inert electrodes that you might use. You can see that most of them are our precious metals. Because precious metals react with so few things, then it makes them strong candidates to be an electrode. So this is going to be an example of an electrochemical cell. Now, as you can see here, this should have been a negative. The problem that we run into is that while our oxidation takes on a standard look, our reduction side gets a little bit more complicated. Our reduction had a lot going on. We had H+ in there. We had our manganate, or MnO4 permanganate, going to our manganese. And so we have all three of those things inside of our solution, right? And so you can see our commas being involved to dictate our different ones. We can also see that this is our reduction process right there. We have that H+ because we had that acidic solution left over there. And then we can see here that this is going to be our cathode. So when you're doing your notation, you just have to remember which one's your reduction, put in anything that's aqueous on one side of it, draw your bar, and then you can put in whatever your electrode is going to be. Primarily, for a lot of theory, everyone uses platinum as their inert electrode. In industry, you get a lot of variety of different ones because platinum is crazy expensive, right? So for right now, if you don't know what to put down for your inert electrode, go ahead and put platinum, right? Later on, if you actually have to build these cells, you generally won't be using platinum because platinum is going to be way too expensive. So a half reaction with a strong tendency to occur has a large positive half cell potential. What that means is that when they're lined up correctly, we should be giving a lot of energy to go from our oxidation to its in the oxidation process, and we should also be either giving or not taking much energy when we go through our cathode process. So the electrons will flow so that the half reaction with a stronger tendency will occur. What that means is that when we're looking at these cells, if we have a copper going to copper 2+, that gives us a positive 0.34 volts. Our hydrogen going to H2 gives us 0. So if we try to set this up for our copper to go into copper 2+ and the hydrogen to make hydrogen gas, that's not going to happen. Right? When we look at the difference between them, we're not going to get the positive one for it to be going in this direction. Instead, we'd want to flip this so that way our copper is being produced instead of our hydrogen, so that we can align those processes up correctly. And so if we look at our zinc and our copper reaction over here, you can see that zinc going to zinc 2+ gives us this 0.76. Copper going to copper 2+ requires this amount of energy right over here. Let me And so if we set up that system that way, while it takes us some energy to oxidize the copper, so while each of these have their own energies associated with them, you can see that zinc much more prefers to go to its 2+ or to oxidize. We get energy out from it versus the copper, which requires some. So when we built our battery, instead of copper being the anode and going through the process, we're really having the zinc be the anode because the zinc is going to give us a 0.76. And then the copper, when it goes the opposite direction, we can flip this as it goes back in that direction, and we're going to be able to make a positive. Now, no half reaction can run by itself. And so what you notice is a lot of them are set up against this standard hydrogen electrode or standard potential. It means that we had to have a 0 mark in order for us to compare whether something is positive or something's negative. And so we run that against the SHE, the She, right? So this is the standard hydrogen electron. So we basically measured that voltage that it takes. We set that as equal to 0, right? So this is under standard conditions. So this is at 1 atmosphere, 1 molarity for its ions. And so when we measured the half cell, we really measured zinc against hydrogen to get that 0.76. In order to get copper's negative 0.34, then we ran that against the hydrogen one as well, right? And so that's how we're able to come up with their values. So their half cell potentials are basically all compared against that hydrogen as its standard. So we'll have positive values and we'll have negative ones. The more positive your value, then the more likely you tend towards reduction. The ones that have oxidation potential, they have a negative value. And normally what we compare them with is we compare standard reduction potentials. So we're looking for them to go from their ions to their solid. So we're looking at their reductions. So one process is basically the opposite of the other. And so if you want to flip it, right, if we want to take our copper and instead of be doing its oxidation, if we want to do its reduction, then we just need to take its voltage potential and we need to flip it. And so this is a chart with all of your standard electrode potentials. It's inside your book. You don't have to memorize it, right? I would give you the values if you needed them, but you just want to make sure you're paying attention to how they're written. Are they written as reductions or are they written as oxidations? Because different places will have them written in different ways. Right? In this case, sorry, I muted myself. This 2.87 lets me know that this fluorine really wants to go to the fluorine ion. On the other hand, lithium down here at the bottom, the lithium ion really doesn't want to go to lithium metal. Instead, our lithium metal really wants to go to lithium ions, and that process would give us 3.04 volts. So the more negative you are, the stronger of a reducing agent you are, because you really want to oxidize. The more positive you are, the stronger of an oxidizing agent you are, because you really want to reduce, right? And so that's how they're set up. So this is a practice one for you to practice going over reducing agent versus oxidizing agent. So think about what that means. So a reducing agent is going to be something that causes the other thing to oxidize. So if we wanted to do that, if we want to cause the other thing to oxidize, or sorry, not oxidize, we want to cause the other thing to reduce. So if we want to cause the other thing to reduce, then we must be oxidizing. So look at your cell. Who is oxidizing? Oxidizing should be on the left-hand side, and so it should be our nickel. And so our nickel solid is the one that's oxidizing to make that nickel 2+. And so nickel is our reducing agent. So when we're looking at our reducing agents and we're trying to compare them, we're looking at our voltages over here. So our best reducing agent means that it oxidizes well. So if we wanted to, we can look at these processes, right? And we can think about which one is going to prefer to do oxidation versus reduction. So our silver right now, it's got our highest value, 0.80. And so when it reduces, it gives us 0.80. So that's great. It wants to reduce. That makes it a very bad reducing agent, right? Because if it's reducing, then it's going to cause the other thing to oxidize instead. So it really doesn't want to oxidize. So this is a good, wants to reduce. So that makes it a good oxidizing agent. So if we're looking for the best reducing agent, we want the thing that really doesn't want to reduce. And so between our nickel or our zinc, we can see that our best reducing agent is going to be our zinc metal, because it's going to want to oxidize to make that zinc 2+. So our zinc metal going to zinc 2+ and 2 electrons is going to give us 0.76 volts. Our nickel, on the other hand, is only going to give us 0.23. So our zinc is going to be preferred over our nickel. Our silver, on the other hand, it so badly wants to reduce instead that it's going to give us a negative amount of energy in order for us to oxidize it. Right? So it's really unpreferred. So our best reducing agent is going to be our zinc solid, as we compare those. Now for your standard your standard cell potentials, what you want to calculate is you want the whole cell to be equal to how much you gain from oxidation and the amount that you gain for reduction. Now the interesting part about E cells is that, unlike Hess's law, you don't have to multiply them if you do multiples of those half reactions. So do not multiply the half cells, right? Because if we do more of that reaction, it just changes the number of electrons. It doesn't change the energy that they have. So it doesn't change the differences. It's like us keep adding in water at the same height. We're going to change the current flow. We're not going to change the voltage of them. So as long as you line up your E cells to be how they should be written, then you just add them together. So a redox reaction will be spontaneous when there's a strong tendency for the oxidizing agent to be reduced and the reducing agent to be oxidized. It means that if they're lined up to go in the correct path, right? Now, the higher on the table of the standard reductions, the stronger tendency to be reduced, right? So the more positive that one was for your reduction process, then the preferred one that's going to be. Now, I feel like this is easier with some numbers. So let's look at our copper and our zinc. So when we're trying to find out which one's going to be spontaneous and non-spontaneous, if we look at our zinc solid going to zinc 2+ and our copper going to copper solid, that gives us a reaction where it's the flip of this one. So that's positive 0.76 volts because our zinc is going backwards. And we get the forward of this one. And that gives us a total of 1.10 volts. So that's pretty good. On this second equation, instead of flipping that bottom one, we keep it as it is, so 0.76 volts. We do get to flip that top one, right? Because now this one, our copper is going to be moving on the other side. So we flip that. And so that becomes minus 0.34 volts, and we become negative 1.10 volts. So a negative means that we need to put in that energy. We're missing that energy. And so this becomes non-spontaneous. Whereas a positive means that we're going to get that energy out. And so we would assume that that reaction would take place. So it would be our spontaneous one. Now that doesn't tell us how quickly or how slowly that would happen, but it gives us an idea about how it's going to go through that process. The last thing is that when you look at your reactions and you want to think about whether or not metals would dissolve in an acid or not, you're really comparing them against the sheet, right? Metals dissolve in acids if the reduction of metal is easier than the reduction of the H+. So if they would rather reduce, right, then we can get them to dissolve. If we can get them to reduce, then their ion reduction is going to lie between the H, below that of the H+. Now, almost all metals dissolve inside of the HNO3, but that's because of a different process, right? What's happening here is this nitrate, this NO3, becomes an oxidizing agent, and it helps the metals dissolve. Right? So instead of nitrate being the same as like our HCl or acetic acid or anything like that, it goes through a different one, because instead of this being about the H+, it's really about the nitrogen being reduced. So if we go back to look at our standard reduction table, this is where our H+ was. And so when we look, we can look for things like our lithium, our potassium, right? All of these ones down here, we would expect to dissolve because they lie below that of the ion reducing. Whereas the ones above it, we expect to not dissolve inside of our acids because they're going to be higher. Because they're going to be higher than our, sorry, there we go. Because their reduction is going to be easier than that of the H+, right? So the higher on that table. So zinc is an example of something that's going to dissolve inside. And our zinc is right down here. Okay. Now there are some more practice problems that you can work on after this, right? So we've covered a lot of different things today. And so one of them is, let's go ahead and work on predicting what our cell potential would be under our standard, or for the following reactions. So look at your oxidation reductions, decide which one should oxidize versus which one reduce. Right? We can practice that one. You can also look at which one of these is going to dissolve inside of nitric acid, but not in hydrochloric. So what that means is you want something that's not going to dissolve based on that H+ rule, because it's going to dissolve in nitric. So almost everything dissolves in nitric. And so we just need something that's above that of our H+, right? So we see gold, which is, where's our gold? Well, we do have our iron down here. We have our lead. We have our nickel. We have silver over here. And then we have our gold, right? Now, that means that we know lead, iron, and nickel are all going to dissolve inside of the metal. And so the only ones that we need to think about is between our gold and our silver. Right? Now, gold and platinum, these two are the only ones that don't dissolve inside of, wrong color. Right? These are the only ones that don't dissolve inside of nitric. We don't even have platinum on this one, so we don't have to worry about it. Right? And so between these two, it should just be our silver. There you go. We'll continue this on Wednesday. We'll get into the next part where we're looking at the electrolysis side of things.